So students, you can see a lot of mirrors around you, different size, different shapes. So we are using the mirror in our day to day practice. Like we are using plain mirror to see our face. We are using the mirrors in the we are using the mirror as the rear view mirror in our cars. We are using the mirror to see the minute tiny objects, and like the dentists are using, like the ophthalmologists are using. So there are so many uses of mirror. So first we'll discuss about the uses of the concave mirror, where we can you just figure out at which place we are using the concave mirror. So we are using the concave mirror in case of the headlights of the car, that is concave mirror. Why we are using the concave mirror? Because it is a property of concave mirror to converge the light. So the light ray falling on this mirror, that is being converged and being focused at a point, and we are getting the light at that point is of high intensity. So we are using that, like we are using these mirror in torches, we are using these for vehicle headlights, we are using these mirror for like to concentrate the sunlight. That is in case of, we had already discussed in sources of energy that nowadays solar cookers are having the spherical mirrors, that is the concave mirror, in order to converge the maximum sunlight falling on that mirror. So there are some figures like in torch, to get the maximum intensity of light, the bulb is very small in a torch, but that is inside that, around that bulb is the concave surface, that is highly polished. So when the small light from that small bulb fall on this concave surface, polished surface, it is being reflected and come out in the form of high intensity of light. Then another is that spotlight used in that photo shoots and movie shoots. Another one is the car headlight we had discussed. Another one is used in case of that shaving mirror. Why we are using the concave mirror for the shaving mirror? As when the object is closed or the person is closed to that concave mirror, the image formed is highly enlarged. So in that case, the person is not able to hurt himself while shaving. Another one is, it is used by dentist in order to see the enlarged image of your teeth. And another one is used by the dish. You are using the dish antenna in order to reflect the light or signal falling on that, and that is being converged and passes through the transmitter. Okay, so there are so many wide uses of the concave mirror. We are using the concave mirror in our day-to-day life. Next one is the convex mirror. Can you just think of the use of convex mirror? Now, what is the property of a convex mirror? The convex mirror produce an image which is virtual and erect and highly diminished, that is smaller than the size of object. So students, we are using convex mirror as the rear view mirror in our vehicles, because the convex mirror gives the diminished image, and it gives, because the size of object is now reduced in the form of image, so we can have a wider view. So we can see a wider view behind us when we are going on a road. Okay, now can you just figure out why the ambulance is written inverted, laterally inverted on the ambulance? So this is your exercise to figure out why the ambulance is written inverted in front of that ambulance. Okay, we'll discuss this when we'll be having your class. Okay, so in this figure you can see that we are having a rear view mirror of a car, Rear means that can see the backside view. Okay, so in this figure you can see that we are having trees as well, we are having the wide view of road, we are having the view of field. So in a small mirror we can have, or we can see so many objects, the clouds, the tree, the road, the fields. So this is the speciality of convex mirror, to diminish the size of object, so the image formed is diminished. Now after the uses of the convex mirror, after the image formation of the spherical mirrors, let us figure out the Cartesian coordinate system for used for the spherical mirror. Now what is the meaning of that Cartesian coordinate system? At you had studied in your mathematics, that is, we are having Cartesian coordinates, Cartesian geometry, like we are having x-axis, we are having y-axis. Now on that x and y axis, what we are doing, we are observing the things. Okay, so there is a sign convention for that, that we are having 0 on a number line, or on that x and y axis we are having origin, that is 0 position. On the left side the numbers are negative, on the right side the number are positive, upside the number are positive, and downside the number are negative. So similarly, a Cartesian system sign convention is also followed by the images formed by the spherical mirrors. And the first Cartesian sign convention is that this is the assumption of the sign convention, that the object is always placed on the left side of the mirror. This is sign convention. Although we can place, in real life we can place the object at any side, that is the right side or the left side, but in this case we are considering that this is the rule, that object is always placed on the left side of the mirror, and light is always coming from the left side and going towards the right. That is, if the object is at left, definitely the light will also goes from left to right. Then second sign convention is, all the distances parallel to the principal axis are measured from the pole. So we are measuring the distances from the pole, that is, the radius of curvature is distance between pole and the center of curvature. Okay, so all the distances are measured from the pole towards the left, towards the right, parallel to the principal axis. Third rule is, all the distances measured to the right of the pole are taken as positive, and the distances measured towards the left of the pole are taken as negative. Just similar as the number line. As in case of number line, the numbers towards the left of the 0 are negative and towards the right are positive. Similarly here, our pole is the reference point and the distances towards the left side of the pole are taken as negative, and to right they are positive. And keep this thing in your mind, that the object is always placed on the left side, so the object distance will always be negative, irrespective of the types of mirror, irrespective of your types of the lenses. In every case, the object distance is always negative. The next thing is about the height, the size. The height measured upward the principal axis is taken as positive, whereas the height downward the principal axis are taken as negative. So as the distances above that origin, in case of that Cartesian or the axis, y distances above the principal axis are positive and the y dash distances below that origin are negative. So similarly it is the case with the mirrors as well. So you can consider the case of the concave mirror. In this concave mirror, we are having a principal axis passing from center of curvature to the pole of the mirror. Now in this figure you can see that the arrow showing the direction of incident light, and the light is coming from left and going towards right. Okay, now The distance between F and P is the focal length, you know that, and this is negative. Why? Because this is on the left side of the mirror. So we know that distances, all the distances on the left side of the mirror are negative. So our radius of curvature will be negative, our focal length will be negative, okay, and the object distance will also be negative. Now depending upon the position, we will get the image distance positive or negative. So in case of concave mirror, only one case is that in which the image formed is positive, and that is the case when the object is placed between the principal focus and the pole of the mirror. Okay, so this is the discussion about the distances. Now if we consider or see the figure that the height of object above the principal axis are taken as positive and the height or the size below the principal axis are taken as negative. So what we conclude? In case of concave mirror, the real and inverted images, okay, the height of real and inverted images, that is below the principal axis, are always negative, and the height above the principal axis, that is the case for virtual and erect image, are taken as positive. So similarly we can consider for the convex mirror. Again in this convex mirror we are having a principal axis, P is the pole. Now you can see from this figure the center of curvature, the principal focus for a convex mirror lies on the right side. So the focal length will be positive, the radius of curvature will be positive for the convex mirror, and the direction of light is coming from the left going towards right. Again the object distance is negative, okay, and in case of convex mirror the image is always above the principal axis, so the height of the image will be positive, okay, and the distance of image is also positive, because in case of convex mirror the image is always formed on the right side of the pole. So the image distance is always positive, object distance is always negative, and focal length is always positive for a convex mirror. So after these sign conventions, we'll find out a rule in order to figure out the relation between the object, the image, and the focal length. Okay, so that relation between the object distance, the image distance, and the focal length of a given mirror is known as the mirror formula for a spherical mirror. So what is a mirror formula? Basically the mirror formula is the relationship between the object distance, symbol for that is U, the image distance V, and the focal length F, and this can be expressed as 1 upon U plus 1 upon V is equals to 1 upon F. So that is 1 upon the object distance plus 1 upon the image distance is always equal to 1 upon the focal length for a given mirror, irrespective of that the mirror is concave or convex. Okay. Now, so this is the mirror formula. Now let us figure out in both the cases whether the image formed is magnified or not, or how much the image is magnified as compared to the size of object. So what is magnification for a spherical mirror? Magnification for a spherical mirror is basically the ratio of the height of the image formed to the height of the object used. Okay, so it is expressed as height of image divided by the height of object, and that is HI, that is the height of image, divided by HO, height of the object. Now this is the relation between the magnification and the size or height of image and object. There is another relation for the magnification, and that is in terms of the image distance and the object distance. So the magnification produced by any mirror is the ratio of the image distance to the object distance, that is magnification is equals to minus V upon U. So we are having a relation M is equals to HI upon HO, that is equals to minus V upon U. So till this topic we had covered about the reflection of the mirror, whether that is the plane mirror, that is the spherical mirror, concave or convex. Then we derived the sign conventions for solving the numerical problems based on the mirror formula and the magnifications produced by the spherical mirror. Our next topic will be the refraction of light. Students, our next topic is refraction of light. Okay, so what is the basic difference between the reflection and refraction? In case of the reflection, we need a highly polished surface or highly polished glass on one side, and in case of refraction we just need a transparent object. So light is always being refracted through a transparent object, whether that is a glass, whether that is a plastic object, whether that is you can say a translucent object. So in all the cases the light is being refracted, means the light is passing along that object. Okay, so what is refraction? So there are two cases. One case when the light is incidenting perpendicular to the surface of that transparent object, and another case when the light ray is incidenting obliquely. Oblique means at an angle, at some angle with the surface of that transparent object. So when the light is incident perpendicular to the surface, in that case the light goes straight along the same path. But if there is an angle between the incident ray and the surface, in that case there is always bending of light. What does it bending means? Bending means the light ray is now not going along the same path. It is either being shifted towards the normal or away from the normal. So what is the phenomenon of refraction of light? According to refraction of light, when the light ray travels obliquely from one transparent medium into the other, it always get bent, and the bending of light is called refraction of light. As we consider a case of air, the light is in air and the light is traveling from air to water. What happens? As we had discussed the case of that glass was filled with water and we were having two straws. So when the straws were dipped, in that case there is bending in the straws. They appears to be cut at the surface of that water. This is because of the phenomenon of refraction. Okay, so there are two cases. One case is when the medium or the light ray is going from rarer to denser, and another case when the light ray is going from denser to rarer. Now what is the meaning of that rarer and denser? Rarer meaning medium is that in which the density of the particle is less. The particles are rarely, or they are placed at a far distance from each other. Okay, and a denser medium is what? In which the density of particle is very high. So the particles are placed very close to each other. Now why the bending of light takes place? Let us first discuss how the bending takes place. So first case, when the light ray is traveling from rarer to denser, in that case the light ray is bent towards the normal. And the second case, so you can see from this figure, we are having a glass slab. Okay, so upper portion, that is why it is air, and another one is glass. So air is rarer medium and the glass is denser medium. What is happening? We are having a normal n dash. Light ray AO is coming in air and through O it is passing inside that the glass slab. Now what is happening? The incident ray AO at point O, after being refraction, is bending So you can see from the dotted line, that is the original direction of the incident light. But the red ray shows the actual path, and this is a refracted light. Now you can see from the figure that the light is being bent from its original path, and the bending is towards the normal n dash. Okay, so this is the case when the light is bending from the rarer to the denser medium. Now again we are considering the case when the light ray is traveling from the denser to rarer. Now this is the case when the light is traveling from air to glass. Now as the light enter in glass, it definitely will come out through the glass, because the glass is a transparent medium. So when the light ray is coming from glass to air, in that case there is again bending of light. Now from this figure you can see that the light ray AO is coming from the glass to air. Now the dotted line again represents the original direction of that light, but the light is being refracted in the form of OB, and you can see that OB is going away from the normal and n dash. So here in this case the bending is away from the normal. Now so these are the two cases when the light ray is going from rarer to denser. Another is when the light ray is going from denser to rarer. Now the bending takes place. What is the basic cause of that bending? The basic cause of bending is the variation in the speed of light. As we had already discussed that the rarer medium is one in which the density of particle is less. So the light is now interacting with less number of particles in a rarer medium. So if it is interacting with less number of particles, it means there is no interruption in the speed of the light and it is going speedily. But if the light ray has to interact with the number of particles, so because of that interaction it slows down, and that is the case for the rarer medium. When the light slows down, it is not going originally from its original direction and it is bended towards the normal, being slowed down by the particles. And you can understand this thing with the point that if I'm saying one student to go straight along a straight direction with a black strap on his eye, so what happens to the speed of that boy? If the boy is going straight without any interruption, no one is coming on his way, in that case the speed is more for that boy. That boy will cover the distance, will go straight along the same path, and the speed will be good. But what if there are 2-3 boys again to interact with that boys? So when the boy is interacting with other boys, what happens? The boy will stop for the moment, discuss something, then move further, again interact with the second one, then move further. And what is happening? Ultimately the speed of boy is slowed down, and it might possible that the boy will get divert from its path. Now instead of 2-3 boys, if I'm saying that there are 10 other students to interact with this boy, in that case what will happen? Again the speed of the boy will slow down. So what we are understanding from this, that similarly it happens with the light. If the light is going from rarer medium, less number of particles are to interact with light, hence the speed is not affected much. But if the number of particles are increased, if the medium is denser, in that case the speed of light, because of interaction with the particles, slow down and it bends towards the normal. Okay, so this is how the bending takes place. Now let us consider the case of refraction through a glass slab. As in these two figures, we are considering a glass slab. In one case the light is going from air to glass, other case the light is going from glass to case. What if we combine these two figures? So that is the case for the refraction of light through a rectangular glass slab. Now in this case, again we are considering a glass slab. You can see from this figure, N1, N1 dash is the first normal at point O. AO is our incident ray from the medium 1, that is air. Our medium 2 is glass, so air is rarer medium, glass is denser medium. Now AO is incident at point O being refracted. Now as the glass is denser as compared to air, the ray of light after refraction bend towards normal, that is N1, N1 dash, and this is our refracted ray, and this is OB. Now the dotted line represents the original path of the incident ray, and you can observe that the refracted ray is bending towards the normal and going away from its original path. Now again what happens when the light ray is passing through the glass slab? At the edge, again it reaches a point where it has to travel from glass to air. So let us consider that point is B. Again we are considering at point B a normal, that is N2 and N2 dash. Okay, so after being refraction through this point, the light ray emerge out in the form of the ray BC, and this ray BC is now bending away from the normal N2 and N2 dash because air is rarer as compared to glass. Okay, so now what we are observing, that AO is incident ray, OB is refracted ray, and BC is the emergent ray. I is the angle of incidence, R1 is the angle of refraction, and E is the angle of emergence with which the light ray is coming out of the glass slab. Now R1, R2 both are same because of alternate angles, and N1, N1 dash and N2, N2 dash being parallel to each other. Now AO, LE is the original path of the incident ray, and it emerged out as BC. Now what we are observing, that there is a distance between this original and the emergent ray, and this distance is known as the lateral shift, means the light ray is shifted from its original path because of refraction through the glass slab, and these two rays are parallel to each other, and the angle of incidence is equal to the angle of emergence for the ray passing through the glass slab. So these are the points to consider when a ray of light passing through a rectangular glass slab, it bends twice, one at air glass interface and another at glass air interface, and the emergent ray is always parallel to the incident ray, and it is displaced through a distance which is known as the lateral shift of the ray. Now after refraction through the glass slab, let us conclude the laws of refraction of light. And what are the laws of refraction of light? Again we are considering the glass slab, and in this figure just simply we are having a normal represented by the dotted line, and incident ray meeting or touching this interface at O and being refracted. Now with normal, the incident ray is making an angle, that is angle of incidence, and with normal the refracted ray is making an angle, that is angle of refraction. Okay, so our first law is like that of law of reflection. Similarly, the first law of refraction is as that of reflection. The incident ray, the refracted ray and the normal, at the point of incidence, they all lie in the same plane. Okay, and the second law is the ratio of sine of angle of incidence to the sine of angle of refraction is always a constant, and that constant is known as the refractive index of the medium, and this law is also known as Snell's law. So what is Snell's law? Sine of angle of incidence is equals to sine of angle of refraction, and that is a constant, that is n, which is known as the refractive index. So basically refractive index also tells us about the density of the medium. The medium having greater refractive index is more denser as compared to the medium whose refractive index is less. Okay, so for reference we always take refractive index of that air or vacuum is 1. With respect to vacuum, we find out or figure out the density of objects. Okay, so the refractive index of vacuum is 1. The refractive index for glass is 1.33. Refractive index for water is 1.4. Refractive index for your diamond, that is very denser. Okay, so that the refractive index for diamond is 2.42, and so on. So each and every medium which is having density is having its own value of refractive index. So after the refraction, we'll study more about the refractive index. So we know that according to Snell's law, the refractive index is sine of angle of incidence to sine of angle of the refraction. But there are so many other formulae for the refractive index. So first one is the refractive index is equals to the speed of light in vacuum or air divided by the speed of light in medium. We know that the speed of light, the symbol for speed of light in vacuum is c, and its value is 3 into 10 raised to power 8 meter per second. And here v represents the speed of light in vacuum. So this is the ratio of speed of lights. Another relation is, if we want to find out, this is the case for absolute refractive index. If we want to find out the relative refractive index, what is the meaning of relative? Relative means refractive index of one in relation to the refractive index of the other. Means how much one object is denser as compared to the other object. So the relative refractive index of a given medium 2 with respect to medium 1 is the ratio of speed of light in medium 1 to the speed of light in medium 2. That is n, refractive index of 2 with respect to 1 is equals to v1 upon v2. That is the ratio of speed of light of two media. Now, after this, the case of slab, after the laws of refraction of light, our next topic is the spherical lenses. So like the spherical mirror, we are having two types of spherical lenses. One is concave, another one is convex. Like the mirror, one is converging and another type is of diverging type. So before discussing the property of converging and diverging, let us first discuss about the types of spherical mirror. Okay, so what is a spherical lens? Lens is basically a transparent material which is bounded by two surfaces, one or both of which are spherical. It may be plane surface, it may be spherical surface. Okay, so there are two types. One is your convex. This is a converging lens in which the light rays are meeting actually at a point after being converged through the convex lens. So another one is the concave. Now let us see the figure for this convex lens. In this case, we are having the light rays which are coming from infinity. After being refracted through the lens, they are meeting at a point, and that point is the principal focus. and the distance between O and F. Here O is the optical center and F is the principal focus. This distance is known as the focal length of the principal focus. In the case of mirror, we were considering the center as the pole. Here in case of lenses, in order to differentiate, we are considering the center of given lens as the optical center. Another case is concave lens. In this case, the light rays being diverged after refraction. They are not meeting, they are being diverged. But when we produce these, they appears to meet at a point on the same side, and that point is known as the principal focus for the concave lens. And as you can see from the figure, the light rays are coming from the left, they are parallel to each other. After being refracted through the concave lens, they are being diverged, that is, they are going apart from each other, they are not meeting at any point. So in order to get the image produced by the convex lens, we produce these diverging rays in opposite direction as shown by the dotted lines, and they appears to meet, they are not actually meeting, they appears to meet at a point that is known as the focus, and the distance of this focus and the optical center of the convex lens is known as the focal length for this convex lens. Now, after these two main types of concave and convex lens, there are so many other types of lenses exist, and these are basically the combinations of the lenses. So the types of lenses are: number one, there are three types of concave lenses. The first figure is biconvex lens. So in these figure of convex lenses, we are having first as biconvex. Bi means the two faces are convex, bulged out. Okay, so this is biconvex. Both the faces are bulged out, both the faces are convex. The second figure is plano-convex lens. As you can see from the figure, the one left side is bulged out, that is the convex, and the other side is straight, that is plane. So that's why this is known as the plano-convex lens. Okay, after this plano-convex lens, our next type of lens is concavo-convex lens. Now left side is convex, it is being bulged out, but the right side is bulged in. There is a depth in this side. So this is concavo-convex lens. Similarly, the types of convex lens, there also exist the types of the concave lenses. The first one is biconcave lens, and you can see from the first figure, both the faces are concave here, they are bulged in, dipped in. So in this case, the center is thin as compared to the outer edge of this biconcave lens. So both the faces are concave. Second figure is plano-concave lens. In this case, the left side is concave, but the right side is plane. Hence, the name is given plano-concave lens. And the last one is convexo-concave lens. In this case, the left side is concave, okay, but the right side is convex. So this is a combination of concave and convex lens. So these are the basically types of lenses. After discussing the types of lenses and before forming the images produced by these different types of lenses, we'll discuss about one important thing that is to be memorized. That is, we are having two foci for the lenses. Bifocal means there are two focus. Okay, so two foci. One is known as the principal focus, another one is known as the second principal focus. So one is first principal focus, another one is second principal focus. As you can see from this convex lens, the figure is this. Now we are having a point F1. If the light rays are incidenting from F1, they are passing through the lens and they are going straight. So this is the rule that when the light ray are going from the focus and they emerged as parallel rays, so that point F1 is known as the first principal focus. So the first principal focus for convex lens appears on the left side, and the focal length F1, that will be negative as per the sign convention. Now in case of concave lens, you can see from the figure, we are having a biconcave lens. The light rays are incidenting on this lens, and after being reflected, they are going parallel to each other. But when we are producing these rays, they appears to meet at a point F1, and this point F1 is on the right side, and this is known as the first principal focus of the concave lens. So there is a difference between the first principal focus for the concave and convex lens. For convex lens, the first principal exists on the left side of the lens, and in case of concave, it is on the right side of the concave lens. And next is the second principal focus. Now what is the second principal focus? As we know that both the faces are transparent, so both the faces are having the focal length. So one is the principal first and the second one is the second principal. So as we can see from the figure, the light rays are coming parallel from the left and they are meeting at a point that is F2. They are actually meeting at a point that is F2, and that is the second principal focus for the convex lens. And similarly, when the light rays are coming parallel to the principal axis after being refracted, they appears to meet at a point that is known as the second principal focus for the concave lens. Okay, so the first principal focus lie opposite to the second principal focus for the lenses. After this, we will study about the refraction produced by the lenses. As we had studied for the reflection of the spherical mirrors, there are some set of rules in order to get the image formed by the mirrors. Similarly, for the lenses, we are having some set of rule in order to produce or get the images formed by the lenses. The first rule is when the light rays are parallel to the principal axis, means the light rays are coming from the object which is at infinity and they are parallel to the principal axis. So in case of convex lens, the light rays parallel to the principal axis, after being refracted, they pass through the focus, that is the second principal focus of the convex lens. And you can see it from figure that the light ray is parallel to the principal axis. After being refracted, it is passing through the F2, and F2 is our second principal focus for the convex lens. And in the second case, in case of concave lens, the light ray appears to diverge. Okay, after being diverged, it appears to be passing through the principal focus, and that is the second principal focus for the concave lens. Now, the second rule is the light rays are passing through the focus. So this is the case when the light rays are parallel and after being refracted, they are passing through the focus. Now in the next case, we are having the light rays are passing through the focus. In this case, when the light rays are passing through the focus after being refraction, they goes parallel to the principal axis. Okay, both in the case of the concave as well as the convex lens. You can see from the figure, the light ray is passing through the focus F1. After being refracted, it is being refracted and goes parallel to the principal axis. And in the second case, you can see for the convex lens, the light ray after being refracted is being going parallel to the principal axis. Now this light ray is coming from the left side, but it appears to meet at f2. So we are saying that this light ray is basically going from the focus of this concave lens and it is going parallel after being refracted. And our third rule, that is, if the light rays are passing through the optical center. So for this case, irrespective of the type of mirror, whether that is your concave lens, whether that is your convex lens, whether that is biconcave, biconvex, whether that is plano, whether that is combination of concave or convex, irrespective of the type of lens, the light ray which is passing through the optical center, it always goes along the same direction without any deviation, that is without any bending. So here we are considering the case for the convex lens. We are having the two foci f1 and f2 and the light ray is passing through the optical center, that is O, and going straight. Similarly for the concave lens, again the light ray passing through the O, that is the optical center, is going straight without any deviation or distortion or bending. So this is about the set of rules for the refraction of the light through the spherical lenses. After this we will study about the images formed by the concave lenses, the convex lenses, the lens formula and the power of the lens.